effect transistors, design, modeling, and simulation, which is published by the Wiley IEEE Press. He has also published several peer-reviewed articles on topics including semiconductor device design and modeling, neuromorphic computing, and hardware security primitives utilizing emerging non-volatile memories. He is an editor of IET Technical Review and review editor for Frontiers of Neuroscience, Neuromorphic Engineering and Frontiers in Electronics, Integrated Circuits and VLSI. He is also a member of IEEE and the vice chair of IEEE EDS UP section. He also appeared in the list of golden reviewers for IEEE transactions on electronic devices and IEEE electron device letters from 2016 to 2020. So on this note, I'd like to invite Dr. Shubham Sahay.
Thank you so much, Dr. Abhishek, for this comprehensive introduction. And I'm extremely grateful to Dr. Shubham Sahay for giving me this invitation and allowing me to speak before you. So, can I start sharing my screen now?
Yes, sir. You can please start sharing, sir.
Okay, so I'll just do that. So, is my screen visible?
Yes, sir. Your screen is visible. Please move one slide, sir, so that we can see the visibility.
Okay.
Yes. Yes, sir. Screen is moving. You are all set, sir. You can.
Okay. Thank you so much. So, good morning, everyone. So, in this talk, I will be presenting some of the latest research from our group at IIT Kanpur. And the topic that I'm going to speak on is exploiting neuromorphic networks to predict the future based on the past. So this title may look a little bit fancy, but it's not something which is a sci-fi thing or something. So before I get into the details of this neuromorphic networks and how can we utilize them to predict something, predict the future, let us get into the details of what is the current state of the art. I mean, what are the things that these neuromorphic networks are capable of? So to start with, let me give you an example of this automated bicycle, which is actually embedded with this transit chip. So this bicycle can balance on its own. It can listen to your voice commands. It can turn left, turn right as you say it to do. It can even follow you when you run. So this is not a scene from a sci-fi movie, but it's a video from Peking University which developed this transit chip. So this transit chip is nothing, but it has got 4 neuromorphic networks. So it has 4 chips enabling 4 different neuromorphic networks. And with that, you can see that it is able to do wonderful tasks, right? So it has got multiple sensors and transducers that kind of take information from the environment and give to those neuromorphic chips. All those neuromorphic chips are integrated in 28 nanometer process. And if you look at their throughput, it's significantly high. So their throughput is like 1.3 tera operations per second. So what do I mean by operation? So one operation is basically one logic operation or one vector by matrix multiplication or one accumulation and multiplication, something like that. One operation is one multiplication, one accumulation, or a logic operation such as XOR or something. So these chips can perform around 1.3 into 10 power 12 such operations per second, which is significantly high. However, if you look at their operating frequency, this is only 300 megahertz. So typical operating frequencies of our CPUs or GPUs, that is in the range of some gigahertz, right? When you purchase a laptop or a computer or a workstation, you see that typical RAM speeds or clock speeds of the RAM are in 4.1 gigahertz and so on. However, these chips, their operation frequency is only 300 megahertz, and despite that, you can see that they're performing so well. The reason for this high throughput, even when the operating frequency is low, is because of the massive parallelism that these neuromorphic networks provide you. So what are those 4 neuromorphic chips which are integrated in this bicycle? So we have one chip which is performing CNN or convolutional neural network, which is used for image processing and object detection, like it is detecting the radar right now. Then there is a CNN chip, which is continuous attractor neural network, that is used for human target tracking. Then this also houses a spiking neural network chip. So spiking neural networks are most biorealistic kind of neural networks because they process information with the help of train of spikes, and that is something how even the information is being processed in a human brain, and that is used for voice command recognition. And then they also have this multi-layer perceptron for altitude balance and direction control. So this is kind of used to control its balance and all. And this MLP or multi-layer perceptron or classifier is the most common deep neural network primitive that you can encounter in this world. So these are the 4 neuromorphic networks that these chips enable. So with this kind of introduction to this field, let me go through the brief content which I would like to cover in this talk. So I would start with neuromorphic networks. What exactly happens there? Then I would talk about feed-forward neural networks, which is one class of neuromorphic networks. And after that, I'll talk about neural networks which have a feedback as well. And those are typically known as recurrent neural networks. Once I have talked about these neuromorphic networks, I'll talk about the need for non-von-Neumann computing and what is the need to accelerate these neural networks, what is the need to develop efficient hardwares or I would say dedicated hardwares to perform these neural network applications or neuromorphic network applications. Then I would talk about resistive RAMs, which are one of the most promising kind of devices, emerging devices, which may be used for generating an ultra energy efficient and ultra area efficient accelerator for these neuromorphic networks. I'll talk about their operating principles, and after that, I'll tell you how can we map these neuromorphic networks, which are kind of software entities, onto RMM crossbar arrays, which are hardware. Then I'll also talk about some hardware-aware algorithms by which you can train these RMMs according to the software needs. And after that, I'll talk about this long short-term memory based on passive RMM crossbar array, with which you can predict the future based on the past trends. And I would conclude the talk on that end. So, needless to say, we are living in an era of artificial intelligence revolution. It has got multiple applications, and these applications have been rising rapidly. Now, the moment we talk about AI, the inherent question that arises is: has India lost the bus? So, is India, self-sufficient in terms of this AI? The answer is yes. So, India hasn't missed the bus because Niti Aayog has got a special, section for this, which is dealing with this national strategy for artificial intelligence #AI for all. So, we are still in the race, and we are one of the leaders as well. If you look around yourself, these AI primitives have become part of our everyday lives, right? You use voice assistants like Google, Cortana, Alexa, like rich people use Siri, but we use them in our day-to-day life. And also we have several filters like Snapchat, FaceApp. Faculties may not be using Snapchat, but it's very popular among students. And these are really intelligent. You ask them any question, they'll give you a very prompt response and a very intelligent response. However, if you have observed it carefully, these devices do not work without internet. Reason is that still the processing is done on the clouds. So what happens whenever you speak, okay Alexa, play this music for me, what Alexa does is it first takes in your voice input, converts it into an electrical signal, processes it, then it sends it to the cloud over here. Processing is done on the cloud, that is their Amazon server, and from there the output which it has to go comes back to this Alexa, and then Alexa just outputs it. So Alexa is just a transducer there. It's just a medium for you to connect to Amazon server. Processing is now not done on Alexa. So the thing is, we want these applications to run without the use of internet. We want them, we want our smart devices, our mobile devices to be able to process these applications without having to connect to the cloud. And for such kind of applications, for this capability of edge computing, what we exactly want is, we want a processor, we want a dedicated processor, which can provide you a large energy efficiency and a large area efficiency. There you don't care much about speed and flexibility, because speed you saw already that even at 300 megahertz, all those chips are performing really well, and that bicycle was really a wonder of science, right? So we don't want something which has got very large speed. If we can get it, it's better, but we do not want it essentially. However, for this cloud processing or server processing, it's the reverse, right? We need a very high speed processor. We need a very flexible processor which can process all kinds of applications. However, their energy and area is not that much important, because servers have got huge power backup, right? However, your mobile devices, there the energy is a constraint, especially in IoT devices where they can be put in some remote area having limited power supply or limited battery backup. Then that becomes a really bottleneck. So that was all about edge computing. Why do we want to make devices or make processors which are having ultra large energy efficiency and ultra high area efficiency while dealing with this AI applications? Now let me talk about this neuromorphic networks, which have been the driving force behind this artificial intelligence revolution. So for talking about neuromorphic networks, I'll be taking a very simple example of a feed-forward network, or a multi-layer perceptron, or a classifier. So it looks something like this. So this is simple simple representation of any neuromorphic network. So these circles over here, these nodes, these are known as neurons, and these lines or edges connecting two different neurons are known as synapses. So the example that I'm giving you, it is an example of a classifier or a multi-layer perceptron, which is essentially a feed-forward network, because here there is no connection between the output and these inputs. So these inputs, the neurons at the first layer, they are known as input neurons. Then the neurons at the final layer are known as the output neurons. And in between, whatever neurons are there, they are called the hidden neurons. So what does a classifier do? So you first train it over a set of images, and after training, when you feed it any other image, let's say I fed to this network this image. So it will classify that, okay, it was a panda that you fed. I fed it like this image, it will classify that it was human. I feed this image to this network, it will tell me that, okay, it's a tiger. So that is the main essential goal of a classifier or a multi-layer perceptron. How does it perform it, or what is the basic operation that is being done in this network? So the basic operation that is being performed in this network is a vector by matrix multiplication of the input vector with the synaptic weight matrix. So what happens essentially is, any information that you give to this input network, and how essentially you provide this image information to this network. So these images are composed of several pixels. So each of those pixels have certain pixel intensity. So that pixel intensity is normalized and converted into a number, and then that is passed to this neurons. That number is essentially passed. So what exactly happens? You convert this image, like its pixel intensities, into several numbers, and those numbers are fed to this input neural network. And then initially you randomize these weights in the network, and then what you perform is, you perform a vector by matrix multiplication, which is simply given by this, or a dot product. And before coming to the next layer of neurons, what essentially happens, this vector by matrix multiplication happens, and once the information reaches this next layer of neurons, what this neuron does, it just applies a function on it, or a kind of activation function on this kind of input, which is your vector by matrix multiplication, such as ReLU, sigmoid, tanh, or there are other activation functions as well. So this neuron just applies these filters on it, or activation functions on the input, which is essentially the vector by matrix multiplication. Regardless of what kind of neuromorphic network you're talking about, the basic operation remains the same. It is the vector by matrix multiplication of the input vectors with this synaptic weight matrices. And initially, what happens? Your synaptic weight matrix is randomly initialized, right? So these weights are random initially. But with random weights, you cannot be sure that whatever you are getting at the output is correct. So what people do is, people essentially go for a method which is called training. And in this training, they try to improve the accuracy of this neural network. So what exactly happens in the training? So basically, these inputs are fed to this network. So we have like a training set first. So in the training first, the network knows a priori what is the image and what is the corresponding label. So network knows that if you feed this image, output should be panda. If you feed this image, output should be human. If you feed this image, output should be tiger. So the network knows it a priori. So first, this kind of training set is given to this. So once this is fed, like let's say once this image is fed here, what happens? Its first pixel intensities are converted to numbers. They are fed to this input layer. Then vector by matrix multiplication takes place here. It is fed to the next layer of neurons. Next layer of neurons perform this activation function over this. And then again, output of this neuron is like vector by matrix multiplication takes place with this synaptic weight matrix. Again, it reaches the next layer where again this activation function is implied on it. Then again, vector by matrix multiplication, and at last, you get this label dash out of the network, or the output of the network. So this is kind of feed forward, because the information is fed only in the forward direction. It's not returning anywhere. There's no feedback. So this is why we call it a feed forward network. Now, once the information reaches here corresponding to this image, we just compare this output with this label, which is panda. If we see that these two are not matching, then what we do is we form a cost function, which is essentially telling you how much different this output is from this label, which it should be. And then we find out what is called an error. We perform error calculation, and then we tune these weights, we change these weights to reduce the difference between this label and label dash through a process which is called backpropagation, and it follows the gradient descent algorithm. So at the end of the day, I mean, during training, what happens? You are essentially changing these weights to reduce the difference between the label and the label dash, which you should get, right? So, and the algorithm that is being used is backpropagation, which is based on gradient descent. So let me talk something about gradient descent as well, because it may be new for many of us. So gradient descent, as I told that, I already know that the image that I am passing to this network is of panda. I'm just looking at what is coming at the output of this network. So I can make an, cost function like mean squared function, that is label minus label dash square, which tells me how far this label is from label dash. We can also have some other functions like log logistic functions. But the essential goal of these cost functions is to just see how much close your label is to the label dash. Now, this cost is essentially a function of weights and biases. So I told you that we are changing these weights, synaptic weights, to change this, like to reduce the cost, or to reduce the difference between label and label dash. Essentially, what we want is that the network synaptic weight should be such that label is actually equal to label dash. So essentially, this cost or label minus label dash is a function of those weights as well as biases. So bias, let us just forget about biases for the time being. They are just to improve the accuracy of neural networks. Weights are more fundamental component of neural networks. So let us just assume that cost is a function of weights. And what we are essentially trying to do is we are changing those weights such that the difference between label and label dash reduces. Now, if you go by a simple linear algebra thing, so if your cost is a function of just two variables, let's say v1 and v2, what can you say about the change in the cost when you are changing those variables? So the change in the cost is simply gradient of the cost with respect to the variable times the change in the variable plus gradient of the cost with respect to the second variable times the second change in the second variable. So this is simple, chain rule. Now you can see from here that change in the cost is simply the gradient of the cost with respect to that variable times the change in the variable. So essentially what you're doing is you are changing this weight, which is the variable here, and you are changing the cost just by changing the weights. And we know from fundamental algebra that change in the cost is simply gradient of the cost with respect to weights times the change in the weights. Now change in the weights is something that is in our hand, right? That is in the hands of programmer. So if we change this weight such that it is actually negative in direction to that of the gradient value and it is proportional to the gradient, then what we are essentially doing is we are essentially ensuring that this change in the cost is negative of something which is positive. That is, the change in the cost is always negative. If the change in the cost is negative, we are ensuring that the label and label dash, they are like coming close to each other. So this is basically what is gradient descent algorithm. We change the weights or we change the variable in such a way that they are negative in sign to the gradient of the cost, and by that we ensure that the change in the cost is always negative, or in other words, the cost is always decreasing. That is, our network is training perfectly well. So this is about training of neural networks. Once this network is trained, what we essentially do is we deploy this network in the field and we perform this inference. So inference, what happens in inference? So inference, what happens is, to this network you apply any unknown image. For here, like for instance, here I applied my own image and I look at whether the output that is coming from my neural network, that what is the output that is coming from my neural network. So if your network is trained perfectly, then it would classify me as a human. I didn't get time to train my network perfectly, so it classified me as a panda. So the thing is, if you train these networks properly, if you tune these weights, if you adjust these weights properly of a neural network during the training, then during the inference, you are sure that whatever image you are giving it, it will classify it into a particular family, and that belongs, like that family would be the true family. I mean, it will perform really well in that application. And as I say, some nets are even more accurate than humans. You must have heard about some alpha supercomputers defeating the world champion in AlphaGo game in chess and so on. So these networks, if trained properly, they can be really efficient, but only on some application. I mean, in general, the general intelligence of human beings cannot be challenged by these machines, but for some particular applications, you can always depend on them. They can always beat you in some particular application. But the overall cognition or the overall intelligence, human beings can never be defeated by any machine. Because our brain is such a beautiful thing. I'll discuss about that as well. So just by this, I wanted to make sure that you guys understand what exactly is training, what exactly is inference, what exactly is gradient descent, because it will be used later. Also, if you look at Google's workload, I mean Google's data center workload, around 95% of Google's data center or Google server is used only for performing these applications. So you can understand that these neural networks, what kind of a heavy usage now they are being done in the industry. And this MLP, which is this thing, multi-layer perceptron, it actually, like 61% of the overall servers of Google, they go on in doing this application. 29% go on doing LSTM, which is the neural network that I'll be talking about. So the main message that I want to pass is around 95% of Google's huge server is being utilized only for these AI applications. And you can understand the amount of power and energy that these kind of servers would be like extracting from the world. So that is actually huge, and that is why we need to, we need to be able to do these applications in an energy efficient way. Okay, so with that, I would also like to talk something more about training. So how do we train neural networks and so on? So let us say that we have this. So let us say that we have this daemon sitting in neuron J of layer L. So how do we classify? So this is first neuron, this is second neuron. Let us say that dot 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 we see the neuron J, and layer L simply means that this is the input layer, and then after the input, it's the Lth layer from the input. So let us say that a daemon is actually sitting on this neuron J in layer L. Now, essentially, as I told, the kind of operation that is being performed in any neural network would be the vector by matrix multiplication, right? So vector by matrix multiplication of this synaptic vector, this synaptic weight matrix with the input vector coming from the previous neuron. So it is Wijl, which is this synaptic weight matrix, into xi L-1, which is the input applied to this L-1th layer of neurons. And then what these neurons do, they simply apply a transformation function on this Yj, vector by matrix multiplication output. Now let us say that this daemon is malicious and it changes this input Yj. Somehow it changes this input by del Yj, right? So this vector by matrix multiplication, this daemon just tunes it by del Yj. Now let us see what is the change in the cost. So change in the cost simply can be given by gradient of the cost with respect to del y times the change in the del y introduced by daemon, right? Now this change, the gradient of the cost with respect to this vector by matrix multiplication, this is a very important parameter and it's known as error of the neuron. Why it is called error of the neuron? Because let's say this daemon changes this vector by matrix multiplication only by a small amount. So this del yj is small. Now, if this gradient of the cost with respect to this VMM is large, then we see that change in the cost would be large, right? So if the change is large, we can say that the neuron was like this neural network was not trained properly because there was a scope for changing the cost by a large amount. On the other hand, even if this del yj is small, if gradient is small, if del c by del yj is small, then this change in the cost will also be small. So this heuristically tells you that the change, whatever change you make in this del yj, the change in the cost will be small. That means network was already close to its optimal value. You cannot change the cost much. So this gradient of cost with respect to this vector by matrix multiplication kind of gives you the error of neuron J in layer L. And as I told, heuristically it gives you the sense of error. Why? Because if it is large, then that means change in the cost can be large and the network is not tuned to its optimal parameters. There's a huge scope for changing the cost. However, if it is small, then it simply means that the change in the cost is small, and as such, the network is already close to its optimal solution or optimal values of weights. So what we essentially do is we try to find out this error. And why do we try to find this error? Because as we discussed here in this previous slide, we have to change the weight such that it is negative and proportional to the gradient of the cost with respect to weight. So gradient with respect to weight is somewhat difficult to find, but we have to find it because we have to tune those weights according to that, right? So gradient of cost with respect to the weight is simply given by this chain rule. It's gradient of cost with respect to this vector by matrix multiplication into gradient of vector by matrix multiplication with respect to weights. So this comes out as error, which is this function, multiplied by the previous layer of inputs. So essentially, what we have done here is we have found out the gradient of the cost with respect to weight, and that is nothing but the error of this layer multiplied by the inputs of the previous layer. And just by doing that, if we now change our weight in such a way that it is opposite in sign to this gradient, we are making sure that the cost function is reducing. So this is how typically training is done for any neural network using backpropagation algorithm and like stochastic gradient or backpropagation algorithm. Now, this is an example of a feed-forward neural network. Now, let me give you an example of a network with a feedback, which is essentially called a recurrent neural network. So here you see that there is a feedback from the output layer to the hidden layer. Not all connections are pointing in the forward directions. You also have a network, like you also have a connection feeding back this output to the hidden layer. So these kind of connections help you to even like include past inputs for your prediction. So let me discuss about that. So these neural networks are essentially called recurrent neural networks. So what they essentially do is they allow the past observations or the past inputs to be used as inputs for predicting even the output at a later time instance. For instance, there is an input coming at time t, right? So that time t input is actually being multiplied by these weights and then coming to this output layer. But this output layer is also sending the output of time t minus 1 to this hidden layer. So here the final output is not only a function of the present input and weights, but it's also a function of the past inputs. So this kind of network allows you to find out or extract temporal correlations in time series dependent data. It also allows you to perform contextual based learning, or in other words, just to keep things simple, what it allows you is to find patterns in series of data. So you have time series data, so it allows you to find patterns in that. And once you have found patterns, then it also allows you to predict those. It also allows you to predict the future, what will happen in the future. So what is so special about these networks? What essentially gives them this power to predict? So there are these, apart from these inputs and weights, there are these states of this neural network. So these cells also, like these RNNs, also have something which is called state, apart from inputs and weights. And these states are actually the entities responsible for storing that contextual information from the past, right? And these networks are extensively used for time series prediction, speech recognition, video recognition, language translation, ECG signal processing, even for stock market predictions, air pollutant predictions, and nowadays they're also being heavily used for COVID-19 case predictions. However, the problem with this kind of networks is you are essentially transmitting these gradient values back to the previous layer. So what happens is, as the number of these recurrent, or I would say feedback, increases, so what happens is these gradients get multiplied with each other, and gradients are essentially a number between 0 to 1. So if you multiply any number between 0 to 1 with a number between 0 to 1, what essentially happens is the final output is actually less than either of the two numbers. So they vanish. The numbers quickly vanish towards a very small amount. So there's this vanishing gradient problem, which is very prominent with this recurrent neural networks. So people came up with another class of these neural networks which do not have these vanishing gradient problem, which is actually called long short-term memories, which would be the kind of theme for this talk. And they are more suited to capture these long-term dependencies, or here I am telling that these can actually store information about 2 or 3 previous trends. But if you use LSTMs, then you can actually store, or you can take information, or you can actually recognize patterns from last 1000 inputs. So that is much better variant of this recurrent neural network. So to give you a practical example of what exactly like these LSTMs or RNNs do. So when you talk to Alexa, let us say you talk to Alexa and you say that, okay, Alexa, play a song where Shah Rukh Khan was dancing on a train. So Alexa will definitely play Chhaiya Chhaiya song. But how does it do it? What exactly happens inside Alexa? So what happens when you speak? Your speech is actually a time dependent, it's a time dependent information that is being given to Alexa. So Alexa basically translates that speech into a data stream, and it sends it to Amazon server. There you have this RNN or LSTM, which kind of takes that data, and it kind of predicts what exactly is the kind of song that the user wants to listen to. So it has got a huge database, and from that it kind of finds out that okay, it's this song from this movie that the user actually wants to listen, and then it outputs that stream back to Alexa, and then it plays. So inside Alexa, it's just doing that conversion of data bit streams, and then it is being sent to Amazon server, and all those things are being done, and LSTMs and RNNs are being used. You don't you just know that it's some AI thing, but now you know that it's actually LSTM and RNNs which are being which are responsible for doing this. Another very important application that has emerged in the recent pandemic time is this prediction of COVID cases. So you have these predictive models from all the institutes. Our institute also has given this COVID Sutra, which is given by Professor Manindra Agarwal of CSE, which is doing pretty good. Here also it's actually using LSTM or RNNs to kind of take in the input from the previous trends and predict the future. See, the prediction may or may not be always true, but the thing that I want to emphasize is RNNs or LSTMs are the things which can be used to predict future based on the past data. Okay, so here I was talking about RNN. Let me go somewhat into details of LSTMs as well. So LSTMs basically consist of a repeating module or a cell. So this is a cell of LSTM, and it is fed by present input X and hidden state, as well as it has got a cell state. So this cell state is something which kind of stores your contextual information. This input is something which is coming from the present time series, and this hidden state is something which this network stores, and that helps us store information about all the previous inputs. So what exactly happens here is the temporal information or the contextual information is stored in the form of this cell state or HCT. All these things are some matrices. Just remember that all of these are some numbers arranged in the form of some matrices. What exactly happens is this cell state or this context, the information that it is modulated by these different gates. So we have this forget gate, we have this input gate, we have this output gate. So these gates are themselves neural networks, and what they do typically is they just tune the contextual information as the network passes through several layers of such cells. So what essentially happens, input comes, and then here you have cell state of the previous cell, right, which was obtained by previous input. So what happens, this forget gate actually facilitates removal of irrelevant pieces of information from this context, and what it takes as input, this hidden state as well as the present input. So based on them, this neural network, which is called forget gate, removes irrelevant portion or irrelevant pieces of information from this cell state and then passes it. Once it gets passed, and based on the information decided by your hidden state and inputs, what exactly happens? This input gate adds some amount of information to this filtered information after this forget gate has been applied. So this cell state first passes through the forget gate where some amount of irrelevant information is removed. Then this input gate, based on the present input and the hidden state, adds some information to this cell state. And after this, what happens? Based on the information provided by this hidden state and input, what this output gate does is it just transforms and identifies the next cell state. So essentially what is happening, this cell is kind of repeating. So this is, let's say, the cell at time instance t, or input corresponding to time instance t. For the input corresponding to time instance t minus 1, we also have a similar cell, and that cell generated a hidden state as well as a cell state or the context information. So now this context information, based on the current input, this context information is being processed. How? So we have these gates, which are essentially neural networks themselves. First, this forget gate kind of removes some irrelevant pieces of information from the past context. Then this input gate adds some new information to that. And then this output gate kind of forms the hidden gate for the next layer of cells and the cell state for next layer of cells. So that is what happens in a LSTM network. Essentially, the architecture that every LSTM has is you have these inputs, these hidden states, and these biases. Then vector by matrix multiplication is performed between these inputs and these different gates, right? These different like forget gate, input gate, and all these output gates. So essentially here also the major thing that is being like the major, I would say, operation that is being performed is a vector by matrix multiplication. Again, you have this like this output hidden state, and after that what happens? We use a fully connected layer. So typically this is an RNN, and here we have a fully connected layer. So we have basically this LSTM where there is a feedback, and after that we have a fully connected layer like a feed forward network which doesn't have any feedback. So, and that gives you the output. So RNN typically consists of these LSTMs as the initial layers which have a feedback, and these fully connected layers which do not have a feedback. However, vector by matrix multiplication is something that is the major, or I would say the prominent operation even here. Now we know that vector by matrix multiplication is a prominent operation in neural networks or in neuromorphic networks. What exactly, why do we need alternate hardwares when we have these GPUs and CPUs? So this figure over here tells you the amount of operation in gigaops, like how many operations all of these neural networks, all of these common neural networks need in order to classify one image into its particular class. So it's basically telling you how many numbers of vector by matrix multiplication is being performed in classifying one image into its particular class, right? So if you look at the numbers, the most common neural networks nowadays, like this Inception, ResNet, VGG 19, VGG 16, they require at least 30 into 10.9 vector by matrix multiplication just for processing one image. And if it is speech processing or video processing, the numbers can go, it can increase dramatically. So it is highly compute intensive because you have to perform, 10 to the power 10 operations, 10 to the power 10 vector by matrix multiplication just for one, simple task of classifying this image into a particular class. Also, the circles here tell you how many parameters, how many model parameters you need to store in order for this neural network to run. So you see that it's at least some megabytes, right? 155 mega, so it's 0.1 giga. So you need large amount of memory also to store these neural network parameters. So this field not only evolved because you had these new data sets, you had these new algorithms like CNN and all. This field evolved because you had the computational power in the form of these GPUs to run these algorithms. And you may be wondering why it is that only GPUs can handle this, because the amount of power that it needs, I mean computations that it performs, it's huge, and your conventional CPU cannot do that. However, is the GPU energy efficient? That is a question that we'll answer next. So the answer to that question is that no, it's not at all energy efficient. This figure shows NVIDIA Turing chip, which is the most powerful GPU from NVIDIA. It performs 8.1 tera multiply accumulate operation or vector by matrix multiplication per second while consuming 36 watts of power. So it's basically performing 8.1 into 10 per 12 vector by matrix multiplication per second when it takes a power of 36 watts. Now your mobile phone or your smartwatch or any other IoT device that cannot deliver a power of 36 watts. So why is it consuming such a large amount of power? Reason being that the inherent architecture here is a von Neumann architecture where your memory and processor are two separate entities. So whenever you have to compute, whenever you have to perform any application, you have to send data back and forth between memory and processor, and sending that data, like that data transfer between the memory and processor, that not only adds to the latency, but it also adds to your energy dissipation. So Google in its server, what it did is they intelligently used this Google TPU. So TPU is tensor processing unit that they developed for this AI application. Tensor processing unit, as you see, they improved its throughput by 92 teramax per second. I mean, here it was 8.1, so they have like almost 10 times higher throughput, but the power almost remains the same. This also takes in 40 watts only. So how Google was able to improve their throughput? They placed this memory as close to processor as possible. So what they did is, close to the ALU, they put these cache memories, and they put the main memory also very close to it. So just by placing memory close to processor, they were able to improve the throughput. So this is called, near memory architecture. So this is non-human, this is near memory. And by that, they were able to improve the energy efficiency, but still, the power consumption was almost the same level. So even these TPUs cannot be installed in your mobile phones or smart watches or smart devices, wearables. So academia then came to the rescue. So they started making these digital inference accelerator ASICs for performing different applications. So we have chips from JLE by MIT and all leading universities now. So these chips basically perform vector matrix multiplication in the digital domain, and they kind of accelerate some particular application like VGG16 or ResNet 89 in some neural network. So each chip here accelerates a particular neural network only. And you can see that, if you look at the energy efficiency, TPU's energy efficiency is 0.43 teraops per watt. That means it can perform 0.43 into 10 power 12 operations for 1 watt of energy. Whereas these, digital ASICs, they can perform really well in terms of energy efficiency. For instance, the sticker can go up to 62.1 into 10 power 12 operations, consuming only 1 watt. So energy efficiency increased. These digital ASICs used all sorts of tricks like dynamic voltage scaling, like exploiting sparsity of the neural networks and so on. But the only problem with these chips is they can only accelerate a particular neural network. For instance, if you install this chip on your mobile phone, and if this chip is made for, let's say, image processing, you can only process images with that. It cannot be used for voice recognition. It cannot be used for speech processing. It cannot be used for any other application. At the end of the day, what a consumer or what anyone wants is a chip which can be able to do all these applications efficiently, right? So the problem with these digital ASICs is that they are not flexible. And even their energy efficiency, although it's huge compared to TPU, it's still very low as compared to our human brain, which shows you an energy efficiency close to 10 power 6 teraops per watt. You can imagine 6 orders of magnitude difference. So what can be done to realize a generalized purpose neuromorphic processor which can accelerate all the neural networks while consuming a small amount of energy? So throughout the discussion, as I also emphasized, this vector by matrix multiplication is the common operation in all these neural networks. Now, since this vector by matrix multiplication is the common operation, if we can accelerate this, we can accelerate all the neuromorphic networks. So that is the goal, and with that goal, this field of neuromorphic computing was started. So what exactly neuromorphic computing means? I mean, that is what I'll be telling you in this slide. So if you look at our human brain, their memory and processor are not two separate entities. However, memory and processing both are happening at the same time and at the same place. As you are listening to this lecture, some amount of it is getting stored in your brain and you're able to process it live, right? So in our brain, we have 100 billion neurons, and each of the neuron is connected to 100 to 1000 other neurons via help of these synapses. So you have like 100 trillion synapses in just 2 liters of space. Imagine the density. Also, it takes only 20 watts of power to perform 1 day's of work. So you can understand, lesser than this physicality and you are doing every day's work with such an efficiency. The part which amazes me the most is that it performs real-time processing even with ionic conduction mechanism. Now, why I talk about it is your electrical connections are all using electrons for transport. Electron speed is quite fast, right? You know that. However, in the brain, how this information is being processed is with the help of spikes, and those spikes are transmitted by ion channels and by a process which is called diffusion. So essentially the information is passed with calcium ions, and you have to kind of make a gradient of these ions in order for this calcium ions to flow from one place to another. So first the gradient is created and then the ions flow. You can understand how slow that process is. And the frequency of operation of human brain is close to some kilohertz. So you can understand with such a small frequency of operation, some kilohertz, we are able to perform everything in real time, and that too with such a great efficiency. Isn't that amazing? And also, neuromorphic computing doesn't mean that we are emulating the brain. Neuromorphic computing, what it does is, it simply takes inspiration from the way brain does some application. For instance, how brain is doing this vision, how this brain is actually learning olfactory response, how we are able to speak. So these informations, we take it from the human brain using neurobiological research, and then we try to emulate this on hardware with our knowledge of VLSI and nanoelectronics. So that is essentially what is neuromorphic computing. We are not emulating human brain. There have been attempts to emulate human brain. Let me talk about one of them. So the figure over here talks about, like, it shows you the Rickens K computer, which is 4th largest supercomputer in the world. So its capabilities are enormous. So it has got 0.7 million processing cores, 1.4 million GB of RAM, capabilities that you can imagine. This was used to simulate 1% of brain, and the results are actually shocking. So to simulate 1% of brain, this device took, or this entire supercomputer took 40 minutes. And that is 1 second of brain's one-day activity. So if you extrapolate this data, it would take 6.5 years to simulate 1 day of brain's behavior. And in 6.5 years, you can imagine how much amount of energy this will drain. So what essentially is going wrong? I mean, where we are going wrong? We are making these supercomputers, and even after making them, we are not able to realize like efficiency of human brain. The problem is brain is not digital. Here in the brain, what happens? It's in-memory processing. That is, it is done then and there. I mean, memory and processor are not two separate blocks. Where the memory is there itself the processing is being done. And the inherent architecture is different, and that kind of architecture is called non-Nonhuman architecture. Now, so we talked about, this entire system that if we somehow accelerate this vector by matrix multiplication, we'll be able to accelerate everything. So how can we accelerate this vector by matrix multiplication and realize a non-Nonhuman computing system using our hardwares? So it's very simple actually. And this idea comes from this cross-point array. And this idea is not new. It was introduced by Professor Carver-Mead in 1980s. So he was a faculty at Caltech and introduced it in 1980s. And he was the one responsible for, bringing this field. So he was making silicon retina with flash memory at that time. You can understand the, intelligence this guy possessed. Anyway, so what exactly is this cross-point array? So this cross-point array is nothing, but here, you have these arrays of wires. So you have these wires going in the horizontal direction and vertical direction. And at the intersection, you have these devices. So between each of those rows and columns, we have these adjustable conductances or adjustable resistances. So what essentially happened, or what essentially Professor Mead proposed, that if we have an array like this, where we have these two terminal devices whose resistances can be varied, connected like this, then if we encode the weights in form of these conductances, so what essentially we are doing is, these weights, we are converting into resistance or conductance and tuning these conductances to that value. And if we encode these inputs in the form of these voltages applied to the rows, then what happens? Essentially, your Ohm's law takes care of the multiplication. How? So this is the weight, this is your input. What exactly is the current flowing through this? It's V by R or V times G. If this is input, this is weight, the current is actually your multiplication, right? It's V times G, input times weight. So Ohm's law takes care of the multiplication and Kirchhoff's law takes care of the addition, right? So if all the currents are coming on this node, they're kind of added. So with the help of physical laws, you can perform this vector by matrix multiplication, and it's essentially a non-Nonhuman architecture also. Why? Because the weights are stored here and you are actually performing computation here with the help of these weights. You are not storing the weights in some memory location and then accessing it and then going to your ALU to perform these operations. Essentially, your weights are stored here and you are performing computation here itself. So this is a non-Nonhuman architecture. However, the problem why this was not so popular until recently was that there wasn't such two-terminal adjustable cross-point device which could store the weight as well as where you can tune the weights, or you can tune the conductance just by application of some electrical pulses or optical pulses. So until recently, this capability was not there. What changed recently? So in 2008, my postdoc supervisor, Professor Dimitris, took over at UCSP. While he was a postdoc at HP, he came out with these two-terminal devices which could actually store the weights for a long period of time, and which could also, where you could also tune these weights by using electrical pulses. So this paper in Nature, Missing Memory Stuff Found, this actually talks about this new class of devices which are two-terminal, where the weights can be tuned. Also, there the weights can be stored for several years, right? So this is something which has changed in the past decade, and it has again created an interest, or it has brought this field again to the attention of the industries, and now all the industries are working like they're investing heavily in this area and they're working day and night to make these neuromorphic chips. So here in this talk, I would be just covering, or I would be just talking about a simple device, which is known as a resistive RAM or aux RAM or RE-RAM. You may know it by several names. So what essentially it is it's a two-terminal device. It's a MIM capacitor. I mean, it's a MIM capacitor, metal insulator, metal capacitor, where an insulator is sandwiched between two layers of metal. And the best part about this insulator is that it can be, like, its resistance can be tuned just by applying electrical pulses on these metals. So it's like a capacitor. However, this insulator is not a perfect insulator. It can change its, it can change its resistance based on the amount of electrical pulse that you're applying to. So here what I'm showing you is a passive crossbar array. So how it is arranged is, you have these horizontal lines which represent your top electrode going like this, and you have these vertical lines representing your bottom electrode coming out of the screen like this. So at the intersection of this horizontal electrode and the vertical electrode, that is here and here, you have RM devices. You have MIM structure and you have RM devices. So in a passive 0T1R crossbar, you have rows of electrodes and columns of electrodes, and in between all of those electrodes, I mean in between or at the intersection of that row electrode and column electrode, you have these RM devices. There's another flavor of this which we'll talk later. However, the best part about this RM device is that it exhibits tunable conductance states, that its resistance can be tuned to any value between its minimum conductance and maximum conductance, or minimum resistance and maximum resistance. So here, as I show you, we were able to tune the conductance of these RM devices, individual RM devices in this array, from 2 microsiemens to 32 microsiemens in steps of 2 microsiemens, just by applying electrical pulses. And the best part about this was, it was stable, or it was showing the same, it was retaining the same level of conductance even when we were measuring it after 1 second. So if we extrapolate it using high temperature measurements, even if you go to 10 years, you will see the same level of information being retained. So this is the best part about this RM device. Now let me talk about its operating principle. So as I told, it's a MIM structure, and it comes in two flavors. We have already discussed about this passive crossbar, where memristors or these RMs are actually at the intersection of these row and column electrodes. We also have another flavor of this RM, where this RM is stacked on the drain of a MOSFET. So this is a MOSFET, and at the drain of it, you have this RM, MIM. So 1T1R is actually better in sense that this MOSFET over here kind of gives you another kind of tuning probe. So the current through this device, the current through this RM is essentially the current through this MOSFET, because they are connected in series. And the current through a MOSFET can be connected by both its drain voltage as well as the gate voltage. So you can actually control the current which passes through this MOSFET and this RM, and hence you can tune the properties of RM in a better way. So that way it's advantageous. But the problem with 1T1R is that the area that it occupies is the same as the area of a MOSFET, right? So that is one disadvantage of 1T1R. So now how exactly this RMs work? So initially we start with this MIM structure, metal insulator metal, which is in pristine state or virgin state. So here, even if you measure its resistance, it will be very high. You won't be able to realize any kind of resistive switching. So essentially, it's it's in the pristine state and nothing can be extracted from this. Now, what people do to make it active is they stress this oxide or insulator layer by applying a huge voltage on this top electrode, or by passing a huge amount of current through this insulator. So essentially, you stress this oxide, you apply a huge voltage or pass a huge current, and then you attain what is known as soft breakdown or forming process. So what essentially happens in this forming? This acts like a Frankenstein's monster, and the moment a huge amount of current is passed, it wakes up and soft breakdown of the insulator takes place. And in soft breakdown, what happens? Oxygen vacancies are kind of created. So once oxygen vacancies are created, there is something which connects top electrode to the bottom electrode, and through that electrons can flow. So its resistance decreases. Now, when you apply a negative voltage on the top electrode, you essentially pull some of these vacancies towards itself, and as such, some of the insulator region is uncovered. So once insulator region is uncovered, then what happens? The device again goes to the high resistance state. It's not as high resistance as it was here, but it goes into high resistance state because there is an insulator between the top electrode and the bottom electrode. Now the best part about this is, if you apply a positive voltage again here on the top electrode, these vacancies will go down towards this bottom electrode, and you again end up having this conduction filament of vacancies between top electrode and bottom electrode, and as such, the low resistance state is again achieved. So just by applying pulses, you can go from low resistance state to high resistance state, and high resistance state back to low resistance state. And the best part about this is, this filament growth and dissolution is controlled by applied electrical pulses, so you can actually tune it to any particular value. So the best part about RRAMs, first, they are extremely scalable. So people have demonstrated 3 nanometer cross 3 nanometer, even 1.5 nanometer cross 1.5 nanometer RRAMs, which is extremely small. MOSFETs cannot be scaled to this dimension. It can be tuned to any intermediate level. The best part is that. And how we do it? We basically do it by using a program verify algorithm. Let's say we want to program our device to this 15 microamps, and our device is at this level right now here. So now device is this at this point. Now we read this state and we find that it's at 7 microamps. So now we know that we have to increase its current level to 15 microamps, or we have to increase its conductance. So to increase conductance, what we do is we apply a positive voltage to form that filament. Then let's say our device reached this conductance state. Then we read the state, we realize that it reached this conductance state. It is still not 15. So what we do, we again apply a set pulse. So the conductance again increases, and we read what is the exact value of conductance. Since it has not reached 50 microns, we again apply another pulse, and it overshoots this. After reading process, we find that it overshoots it. So we have to reduce the conductance. So for reducing, what we do, we kind of apply reset pulses, that is negative pulses. So just by applying this series of pulses followed by read, we know what exactly is the state of this RRAM, and just by tuning these pulse magnitude, or these kind of amplitude, or this pulse period, we can tune it to any particular value in its range of resistances. For instance, we tuned this smiley face onto our 20 cross 20 RRAM crossbar that we had at UCSP. So here the pixel intensities were converted to resistance, and those resistance were tuned accordingly. I mean, all of these dots or all of these squares represent some RRAM device. So we were able to tune the intensities as resistance of these RRAM devices precisely. Here this black dot represents not a mole, but it was a device which was fixed in the off state, and we were not able to remove it or program it. Other good parts about it is that it shows you a very high retention, more than 10 years, and a very fast switching. Problems or challenges with these RRAMs, first, there's a large variation in the set and reset threshold voltage, because this conduction filament formation or dissolution, it's actually a probabilistic process. Every time you're applying same voltage to the top electrode, but you're not sure whether the conductances that you'll realize would be same. Also, there's a huge amount of RTM because the dimensions are pretty small. So what happens, any small amount of trap inside this oxide, it will create a large fluctuation in the current. And this current fluctuation is also because of a competition between recombination and generation. And you can see that I applied same reset pulse for 10 cycles, but the amount of current that I was getting, or the spikes that I was getting the current, that was different. So your response of this device can be different even when you are applying same voltages. Now with that introduction to RRAMs, let me tell you how we can map these neural networks onto those RRAM crossbars. So here I'm taking example of a bilayer neural network where you have only input layer and an output layer. And the kind of data set that I'm talking about is this, where we have 3 patterns, Z, V, and N. And you have, these patterns have been made by flipping 1 pixel. So now what happens exactly is, by ex-situ training, what I mean is we obtain these, weights which are leading to least error between what is shown and what is coming in the software, let's say in Python or MATLAB. And then we are just programming these weights obtained in software onto RRAM crossbar. So that is what is meant by ex-situ training. And how do we map these weights obtained in software to conductances obtained on hardware? So we have this simple transformation where this Gij is simply Gmin, which is minimum conductance of the RRAM, plus the weight value obtained in the software multiplied by Gmax minus Gmin. So sanity check, when the weight obtained in software is 0, your conductance is minimum, and when the weight obtained is 1, then the conductance is maximum. Therefore, weight and conductances are following one-to-one correspondence. Now, one problem with this kind of approach is your weights can be negative in software, but conductance is always positive. Now the thing is, how can we map something which is negative with something which is always positive? So the answer to that is, we use this differential configuration. So in this differential configuration, what we do is, we divide all the weights in software to a positive part of the weight and a negative part of the weight. So if the negative part of the weight is higher than the positive part of the weight is negative. If the positive part of the weight is higher than the negative part of the weight is positive. And corresponding to these weights, we also have two neurons. So corresponding to each weight, we have one neuron. So there is one neuron which actually calculates the vector by matrix multiplication of the positive part of the weight. There's another neuron which calculates the vector by matrix multiplication corresponding to the negative part of the weight. And then overall result is obtained by taking the difference between the two neurons. Right? So by this we can also incorporate negative weights onto positive crossbar with positive conductances. Best part about this scheme is, if same kind of noise or a common noise is injected on both of them, it gets rejected. So now how do we map it? So what we did, we first trained this network in software, we obtained those weight values, we found out what are these conductances value that we want using this transform, simple transform, this. And then what we do is, we simply convert this into positive part and negative part of the weight. This conductance is mapped to this RM over here, and its negative part is mapped to the adjacent column. Similarly, this conductance is mapped here, and its negative part is mapped to the adjacent column. Once we have mapped all of these RMs, once we have tuned all of these RMs, which are at the intersection of these rows and columns, according to whatever weights we obtained in the software, then what we do is we apply inputs. How do we apply inputs? Suppose we have to apply this pattern Z. So what we do is, we convert these pixels into corresponding voltage. So this black pixel corresponds to a positive voltage, positive V. This white pixel corresponds to a negative V. So black positive, white negative, black positive, 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 negative, negative, and then again positive. This is how we convert this input into a voltage, and we already mapped this weight as conductance on this crossbar. So essentially, when we apply this input and when we have the weights, vector by matrix multiplication would be performed here, right? According to this crossbar cross-point array. So we are applying inputs as voltages, and we have modeled these RM conductances according to the weights obtained from software. So essentially, once we apply these voltages, vector by matrix multiplication is performed, and we gain some current from here. So the best part is, I1 plus minus I1 minus, this current yields the output of the first neuron. I2 plus minus I2 minus yields the output of the second neuron, and I3 plus minus I3 minus yields the output of the third layer of neuron. So when we did that, we found out that whenever we presented any pattern from this class of Z, I1 plus minus I1 minus, this was giving us the highest current. When we showed or when we converted these pixels or these patterns as voltages and applied to this crossbar from this class of V, we found out that I2 plus minus I2 minus, this red one, this was providing the highest current. Similarly, when we actually converted these pixels into voltages and provided it to this crossbar array, from this class N, we saw that I3 plus minus I3 minus, that was the maximum current given by this blue. So our network was actually identifying these three classes, and all of this was done in the hardware. So now this was XC2 training, where we were training it in the software and then using it. There's other way around also, where we can tune it in hardware itself. So tuning, we saw that we have to change the weight in such a way that it is proportional to error multiplied by the inputs, right? So we have to calculate this error, and then we multiply with the input, and that is the magnitude by which we have to change this weight, right? So there are different ways of training. First is stochastic. In that, what we do is, for each input that we are offering to the neural network, we calculate this error and XN, and then we tune the weights after application of each input. However, this is not that efficient, because there, the learning is more local. For a global learning or for a better generalized learning, what we do is we perform something which is called batch mode learning, where what we do is we give an input to the network, we calculate this, but we don't change the weights immediately. We store it somewhere. Again, we give the next input, we calculate this, we store it somewhere. At the end of all of when all of these inputs have been provided, what we do is we actually take the sum of all the EN and XN that we stored somewhere, and according to that, we change the weight. Since we are doing that for one batch, it is called a batch mode. However, for both of these techniques, hardware implementation is difficult. Why? Because in hardware, first we'll have to calculate this error, we'll have to store it somewhere, we'll have to store the input somewhere, then we'll have to take a product of it, then sum of it and store that somewhere. And then only we'll be able to change this weight. So it will require a huge peripheral circuit. So typically what we do is we go for something which is called Manhattan learning, where we go for constant weight updates. So what this means is essentially we are not going to, find out the exact value of this or exact magnitude of this weight change. We'll just find out whether the weight that we want to change is whether we have to increase the weight, whether we have to decrease the weight. Finding sign of weight change is always easier as compared to finding the exact magnitude of weight change. So that is precisely what we do here in Manhattan learning. So depending upon the sign of weight update, we apply a pulse of fixed width and duration, and then that changes our conductance by a particular amount. So how do we do that? So this is crossbar array, and RRAMs are here. Let's say we found out that we need to change the weight, the sign of the weight by this according to this matrix. So what we have is we have to increase the weight of first two, reduce the weight of next two, increase the weight of next two, reduce the weight of next two, and then increase and then decrease. So what we do is we can even perform this update parallelly. How we do it? We apply VW by 2, which is the right pulse magnitude by 2 on the column like this. And to the cells where we want to increase the weight, we just apply minus VW by 2. Why we apply minus VW by 2? Because essentially the overall voltage across that would be VW by 2 minus VW by 2 equals to VW. So essentially this VW voltage is it's falling across this RRAM, this RRAM, this RRAM, this RRAM, and this RRAM, and it actually increases their weight. And that is how you apply or you kind of tune the neural networks during runtime. And this is called in situ training because you are doing it on the crossbar itself and not on the software. The problem here comes because of the variations. So what happens is this VW, you are applying same VW to all of these RRAMs. However, their thresholds are different. So the amount by which the weights change in all of these RRAMs is different, and that leads to a loss of accuracy. So this is how basically you train this neural networks in situ. Now let me talk about how did we train the long short-term memory, which can be used to predict future based on the past on passive RRAM crossbar array. So what we did was there's this 64 cross 64 crossbar where there are 64 cross 64 RRAMs. We just divided this RRAM into two sections where we use this 34 cross 60 devices to store the weights for LSTM layer, 15 LSTM layers. And then we had this, fully connected dense layer at the end of it, for which we selected this one column of 1 cross 32 devices. So this 64 cross 64 was partitioned like this. Then what we did is we randomly initialized the weights between 100 microsiemens to 300 microsiemens. As is done in the software, we randomly initialize the weight. So here also we did the same. Now we actually did a hybrid computing here. So what we exactly did was the analog computing was actually done on the crossbar, and the digital computing was actually done in the software, in the digital computer basically. So what are those analog computing parts? So first, initializing of the conductance matrix, that was done on crossbar. Then the vector matrix multiplication was actually performed on the crossbars. However, it's training and test data were fed in the software, then forward pass and all was done in the software. Loss function was calculated in the software. See, all these things can be done in the hardware with the help of peripheral circuitry. But for ease of implementation, we only perform the basic operations, that is vector by matrix multiplication and one-shot conductance update of this RRAM crossbar. That was done in the hardware. Rest, everything was done on the software. So, as I told, the basic operations, that is the vector by matrix multiplication, during both forward pass and backward pass, that is training, was performed on the crossbar. And you can see that, we can tune even this Einstein's image by converting into pixel on the 64 cross 64 crossbar array. So we actually we didn't do that. This is just a representative of how the weights can be tuned. But this is how the procedure that we used. Even in that, we were able to tune the weights very precisely. And then we performed in situ training of weights using Manhattan rule and mean squared loss function. So Manhattan rule, I already told you, right, that instead of looking at the magnitude of the gradient, we look only at the sign of the gradient. And that is what we used for training this passive crossbar array. Now, what we obtained was that, this LSTM, when implemented on this passive RRAM crossbar array, which is shown by this, blue line actually, yes, this blue line is passive crossbar implementation. This yellow line here is your active crossbar implementation, that is 1T1R implementation, which Hewlett Packard company already did. And this dark blue is your software prediction. You can see over here that this is a mean square loss function. So the loss function reduces significantly as number of training epoch increases. However, for passive crossbar, it actually reduces to its minimum value within 15 epochs. So within 50 epochs itself, you see that your mean square error reduces and the network achieves optimal value. A fast convergence essentially means that it can be trained very fast and with limited energy, and that is owing to the course weight update in your passive crossbars. Also, if you look at the predictions made by both of the LSTM implementation, so this actually represents the trend of passengers, airline passengers, between years 1949 to 1960. The black curve actually shows you the observation, and based on these observations, we were predicting the future by using active crossbar and by using passive crossbar. So you can see here that the passive crossbar, which is represented by this red line, this actually follows the software predictions really well. So the accuracy that this passive crossbar shows you for this kind of future prediction, that is also quite impressive, and that is similar to active crossbar. And the best part is that if this is the observation, we actually first perform these simulations without considering device variation. But even when we consider the device variation, you can see that the results do not change significantly. It is able to perform or predict these sequences well, even in the presence of noise and device variation. So this kind of implementation is actually resilient to noise and even variation. That is the best part about it. Here we show the evolution of the conductances. So here you have this 64x64 crossbar, and as we train it using in situ, like epoch 1, epoch 20, epoch 80, epoch 140, epoch 200, I mean these are different batches of training. So as we train these devices, you can see that the conductance changes. So each of these dots actually represent your RM device, and this actually color map gives you the range of conductances. So the conductances actually evolve towards the optimal value with training. You can see that. However, if you look at this training without considering device variation, which is case A, and training with considering device variation, you can see that the final conductance maps do not change much, and that is the reason why you have this resiliency to noise and variation. Now, the best part about this kind of passive crossbar implementation was that the energy and area efficiencies were really good. So how do we calculate energy while training? So if we have to, so in Manhattan rule, we saw that if weight needs to be updated, we apply a V write, and if weight needs to be reduced, we apply a V reset or minus V write. So depending upon how the weights had to be updated, we just calculated the energy, which is simply V square by R, right? V square by R into T, or it's V square into G into T. So when we did that for two configurations, that is for passive RM crossbar, where we do not have any selector, and the 1T1R crossbar, where we have a MOSFET, and then at the drain we have a resistor. Then what we found out that energy of passive crossbar was actually 2.8 microjoules after 200 epochs, and that is the energy for training. So this is how the energy evolves after each epoch of training, and this is the cumulative energy. And you can see that considering variations or without considering the variations, the energies are almost same. However, the energy of active 1T1R implementation is 145 microjoules after 800 epochs, or for similar accuracy, this network, our proposed network, takes 2.8 microjoules. However, the 1T1R, which was proposed by HP, that takes 145 microjoules. So you can understand that at least by 2 orders of magnitude, so we are performing better at least by 50 times in terms of energy. So it's like more than an order of improvement in terms of energy when we implement it on passive crossbar array. Also, the area of active cell from chip micrograph is 59 cross 40 micrometer square, and the area of passive RM crossbar that we have is 0.6 cross 0.6 micrometer square. So we have around 3 orders of magnitude improvement in area. So if we implement this LSTM for predicting the future from the data of the past using our passive RM crossbar array, we have, or we can achieve 3 orders of magnitude improvement in terms of area, and more than 1 order of improvement in the energy. you can see how we can go for making this energy efficient RNNs. So to conclude, passive RNN crossbar arrays can be used for realizing compact and ultra low power RNN engines, and then these can be used in your mobile IoT devices. And as we already showed, area efficiency of passive RNN crossbar based LSTM network or RNN network can be further enhanced by integration of 3D RNNs. I mean, the future is like you have this CMOS, on top of that you'll be 3D integrating RNNs, and then on top of that you can even further integrate another layer of RNN. So if you can integrate several layers of RNN on top of each other, its density increases further, right? So by that we can even achieve further, like we can increase the area efficiency even further. Now, some general conclusions. So this domain of neuromorphic networks, it has got something for everyone. For device designers, we need new devices having less endurance, less variability, less non-linearity. For circuit designers, we need to come up with new circuits which can take into account these devices, the interesting properties of these devices. For system architects, we need to be able to find out a particular architecture which can take these circuits as the VMM kernels and then exploit its efficiency. And also, we need several algorithms for, with which you can make these designs hardware friendly. And at the end of the day, what is the main goal? So the main goal is to achieve efficiency of human brain, which is exaflops. So that is the main goal, right? A processor which is having exaflops processing power similar to the human brain. So with that, thank you everyone for boggling your synapses and neurons during this talk. Any questions, feedbacks or suggestions would be highly appreciated. Thank you so much.
Thank you very much, sir, for your kind concern and valuable presentation. Now I request the participants to raise queries if there is. Participants are requested to raise their queries.
Thank you. Hello.
Yeah.
Yes, sir.
Yeah.
Yes.
Thank you, Dr. Sahay. Sahay, that was a very, very good and nice presentation on neuromorphing. I have some specific doubt regarding slide number 5. Could you please present slide 15? Sorry.
Sure. Yeah, I'll do that.
Wherein you have MIM structure, metal insulator, metal structure.
Just a second. So you want the MIM structure slide, right?
Yes, sir. MIM structure.
This one, right? Can you see it?
Yes.
Okay.
Can you make it full slide, please? I'm
Okay.
sorry. I just cannot see it on small screen.
Okay. So.
Oh, thank you. So here, the MIM structure, I see you have a platinum, which is, and you are sandwiching TiO2 and Al2O3.
Yeah, Al2O3 is the barrier here.
Oh, Al2O3 is a barrier layer, which prevents. So, and I also see you are not exactly, I know you worked on the simulation side, but I just wonder, I see TiO2 minus X. That means there is a vacancies of oxygen.
Yes, stoichiometry is.
Each vacancy of oxygen will leave 2 electrons. So that means you are there in that particular structure, that TiO2 is not working as an insulator, but rather it works as an conductor.
Exactly. So not a conductor. It's still not showing very high conductor.
Yes, I understand that, but is there?
We are actually introducing this kind of stoichiometry just to make sure that this forming voltage is small. So even if it were a pure TiO2, if you apply large voltage, it will definitely reach soft breakdown. But to reduce that voltage at which this forming takes place, we are actually playing with the stoichiometry and the annealing conditions. So we properly tune the stoichiometry and the annealing conditions so that the forming voltage is less. It's less than 3 volts.
But if that's the case, if you take pure TiO2, once it breaks down, you cannot further use it. It's always a conducting path. But
that also depends on the way you are doing it. I mean, here, like if you do it using ALD, definitely once it breaks down, you're not able to use it. Right?
Yes.
It's a hard breakdown.
Yes.
So that also depends on the deposition conditions, right? So here we were using sputtering. It was not ALD. Yeah.
Okay. And do you take these kind of volatile effects into consideration while simulations?
Volatile effect as in?
In the sense, if I treat TiO2 minus X, It's not going to be stable forever. Let's say I use for 1 day, 2 day, 3 day, the amount of oxygen
Sure,
vacancies
sure,
is
sure.
variable. So there
Yeah,
is
yeah.
some sort of standard deviation or average
Yes, yes.
values.
So that is what I was saying. So it's a huge amount of noise. RTN
Yes.
is very huge, and the variations are pretty huge. You apply
Okay.
same voltage, you won't get the same amount
Yes.
of current through it.
Yes. Yes.
So those we definitely take into account. Yes.
So do you take that as perturbations, or how do you take
Yeah,
that
we
into?
take it as perturbation. I mean, here we were using a like standard normal function. So we characterized around 3 million devices for,
Okay.
let's say, more than million cycle. And
Okay.
then based on that, we formed the Gaussian function, and we were actually fitting, like we fit that function to our experimental data. That is how we did it.
And this is all works at 300 Kelvin, or does it show any temperature
No, no,
variation?
this was all 300. This wasn't any high temperature measurement.
Oh, okay. Okay. Thank you, Sahay, for the brief explanation. Thanks a lot.
Okay, next participants. You can text your questions in the chat box also so that we can read. Okay, it is with that keeping in mind, it is understandable. We are now it is my privilege to thank Dr. Shubham Sahay for his kind presentation
Okay.
during
Thank
this
you so much.
valuable session. I think this will be makes a collaborative benefits between the design engineers and artificial intelligence engineers. Sure, there will be a great opportunity for collaboration with upcoming trend like artificial and design field.
Hmm.
Hope that it will be go soon. So participants, those who are working in artificial intelligence as well as in design collaboration with designs, are come forward to make collaborative with Dr. Shubham Sahai sir. He is
Sure.
working in this field. Excellent presentation regarding that, which regarding machine training and other things. Really, we are feel privileged to have you in this session, sir. Thank you very much for
Thank you
your
so much.
kind consultation. And
Thank you so
I
much for the invitation.
thank you, sir.
Okay.
And I request the participants to join us back by 11:50. And the next speaker for the session is Dr. K.P. Pandan from IIT Kansipur. We request you to join back by 11:50 p.m. Thank you very much.
Thank you, Dr. Sai.
Yeah, thank you so much for the invitation.
In this, whoever speaker, all are known. In this complete FDP, whoever is presenting, all I know personally. Then, huh? Then,